All right, in this video, we're going to look at double integration and value. So I want you to think back to the definite integral that you surely calculated in either Calculus 1 or Calculus 2, primarily Calculus 1 stuff. When we did an integration with a single variable input function from A to B, the fundamental theorem of calculus said that I can find the antiderivative of f, plug in b, minus the antiderivative of f, and plug in a. But that was sort of the algebraic way to find this definite integral. What did that definite integral actually compute? Hopefully you remember that the definite integral, what it was actually doing, again, algebraically, let's say, for example, we're integrating x squared from 0 to 2. We end up with about a 2.67, or an 8/3, by taking the antiderivative of x squared, which is 1/3 x to the third, plugging in 0, plugging in 2, plug in 2 first, find this number, minus what do you get when you plug in 0, find that number. Again, we get 8/3, which is about 2.67. But what did that 2.67 represent? So when we did the fundamental theorem of calculus, what did this integration represent? Well, basically, if you go back to your Calc 1 notes, the definite integral was finding the area under this curve from 0 to 2 in the case where we're integrating from 0 to 2 under the curve y equals x squared, or f of x equals x squared. And the way it does that is by taking a Riemann sum of a bunch of areas of rectangles. So it approximates the area under the curve with a bunch of rectangles, and then it adds those rectangles up. And then when we take the limit as the number of those rectangles goes to infinity, we get the area under the curve exactly. So the area from 0 to 2 under the curve y equals x squared, so this red shaded area, was what I got when I integrated from 0 to 2 x squared with respect to x. Now we call that the signed area because as long as my function is above the x-axis, it's going to calculate this area as being a positive. But if ever my function goes below the x-axis, then it's going to calculate the area between the function and the x-axis, and it's going to count that as a negative. So we call that the signed area under f of x. Again, this is from x equals 0 to x equals 2. So the definite integral gave me an area under the curve. Now we just did some iterated integrals. And so let's do another one and ask, what does this double integration actually find? Okay, so I'm going to do this iterated integral where I integrate with respect to x first and then with respect to y, and then I will talk about what we just found. So hopefully you remember from the previous video in this series that when we're doing double integration, we start with the inside integration that is with respect to x, and we treat the variable x as my variable, and any other variables, such as y, we treat as constants. So in this case, the integration from 0 to 6 stays there. When you take an antiderivative of 3xy squared with respect to x, you'll get 3/2 x squared times y squared. And we're going from 0 up to y. That means I'm plugging in y into the x value, and then I'm plugging in 0 into the x value. Again, I'm plugging those into the x value because we're integrating this inside one with respect to x. So what you end up with is an integration from 0 to 6 of 3/2. So when I plug in y, I get y squared times another y squared. When I plug in 0, I get 3/2 times 0 squared times y squared. And I'm going to integrate that eventually with respect to y. When I plug in y and I plug in 0, that's what I get. Now, this first part becomes 3/2 y to the 4th. This second part just becomes 0. So that means I'm going to be integrating 3/2 y to the 4th with respect to y. And again, antiderivatives, antiderivative of 3/2 y to the 4th is going to be 3/10 times y to the 5th. I'm going to be plugging in 0 and then plugging in 6. When you plug in 6, you get 3/10 times 6 to the 5th power. When you plug in 0, you get 3/10 times 0 to the 5th power. Three-tenths times 6 to the 5th power is a fairly big number. 2,332.8. 3/10 times 0 to the 5th power is just 0. So I got 2,332.8 as this double integration. So I did a double integration, integrated with respect with x, and then with respect to y, and I got 2,332.8. What does that number represent? Well, it turns out that that number is going to represent a volume. We'll talk about the specific volume in just a second, but it turns out that that number represents a volume just like when we did a single integration, the number represented an area. This number represents a specific value, a signed value, in fact. So this double integral was 2,332.8, and I'm claiming it's a signed value. One way you can think about this is that because we integrated with respect to x, and then we integrated with respect to y, instead of having just one summation here with respect to x, which gives me an area, now I'm going to have another summation with respect to y, and so we're going to add a dimension. And when you add a dimension to this Riemann sum, you essentially get a three-dimensional, you don't just get a rectangle, you get a rectangular solid, like a brick or a long bar. And we're going to add up those long bars. So specifically, here's what's going on. If I have a function that has two variable inputs, and I do a double integration, one with respect to x and then with respect to y, or vice versa, you could do it with respect to y, then x, it doesn't matter. Then we're going to get a summation, but we're going to have a small change in x and a small change in y multiplied times this, which remember is a z value. So we're going to get a bunch of little bars, three-dimensional bars that we're summing up. And when you're adding up three-dimensional bars, that gives you three-dimensional objects, which we're talking about volume then. One way to think of it is you're summing up my height of my function times a little bit of area. Again, if I take x times y, that gives me an area. So it's a summation, it's a Riemann sum dealing in volume instead of dealing in area. So here's the connection. A double integral gives us signed value. If we let z equals f of xy be a continuous function defined over a closed bounded region R in the xy plane, so R is a region in the xy plane, the signed value under f but over the region R is denoted by this double integral. We're integrating over the region R, and we're integrating the function f of xy over the region R. Our integration is done with respect to area. That can be a dy dx or a dx dy, depending on how I set up my integration over here on the left. So that's what's happening. Now let me draw the specific instance that we calculated earlier. Let's talk about what this specifically looks like. So the graph here that I've displayed is the graph f of xy equals 3xy squared, which was our function. You can see that it gets pretty big pretty quickly. Now, it turns out that when I'm talking about integrating over the region from 0 to y, my x values from 0 to y, and my y value is from 0 to 6, there's a specific region of the graph that I'm looking at, namely this green part of the graph. It's not drawn real well, but that's what's going to happen. And then it turns out if you look at the area under that graph, excuse me, not the area under the graph, the whole part under the graph, you'll see that in the XY plane, we went from a Y value, excuse me, from an X value from 0 to Y. So that's X value of 0 to X value of Y, left to right. And then the Y value went from 0 up to 6. And so the total mass of stuff under the green part of the curve, again, it doesn't look very good right now, but that's what it is. This total stuff, the volume of that object is what we had calculated. That was the 2332.8. It was the volume of this object over that region that we described, but under the function f of x equals 3x y squared. Oops, 3x y squared, sorry. There. I was wondering that. So it's this, the volume of that object under this surface, but over that designated region in the XY plane. So it's the volume under a surface. Now here I have another surface drawn. And this is just to visualize what those summations are actually doing. Those little summations are giving me different, the Riemann sums. I'm adding up a bunch of little bars like this. So if I'm looking at the volume under this surface here, which is a really weird surface, what I'm going to do is I'm going to take a bunch of bars, just like this one. This is just a representative bar. And I'm going to add them up. You can see that the height of each bar is determined by the height of the surface. And then each bar itself, if you look at it from above, is just a little square piece. It doesn't look great right there, but that's what it is. So these bars of varying heights, that's what we're going to add up. Instead of adding up rectangles, we add up bars. That's the whole point. And again, I put these bars over whatever region I'm looking at. So if the region is from X from 0 to 2 and Y from 0 to 3, I'm going to fill that region up with bars just like this. Let the size of those bars in terms of their widths and their lengths go to 0. Their heights are always going to be determined by the top where they hit the curve, where they hit the surface. Sum a bunch of those up, and that's going to give me volume. So summing up a bunch of those bars gives me volume over a specific area. And again, I would just, depending on what area, we just make a bunch of bars over through whatever region is bounded out in the XY plane. We've determined in the XY plane. So hopefully that makes sense that this double integral gives you volume, and the reason it gives you volume is because we're adding up a bunch of little rectangular bars. So there it is, double integral, adding a bunch of these gets me my limit, and the double integral of a function gives me the signed value under that function, but over the region in the XY plane. Now, just a little note, if my z becomes negative, we call this the signed value because if my surface goes below the XY plane, then that volume is going to be counted as a negative. So if the surface is under the XY plane, the volume part that is under the XY plane is going to be counted as a negative. If my surface is above the XY plane, then the volume of those little bars are going to be counted as a positive. So let's do an example. Let's find the volume under this curve, the curve x squared plus 3y squared. I guess it should say under the surface, but over the rectangular region where x goes from 0 to 4 and y goes from 0 to 2. So the volume under this surface over the rectangular region described here. Okay, this one is a pretty straightforward setup because when I'm trying to find the value, I know I have to do a double integral. But the hardest part about double integral is setting up the bounds. Here, the bounds on y go from 0 to 2, and the bounds on x go from 0 to 4. So since we're doing it over a rectangular region, I can just integrate x from 0 to 4 and y from 0 to 2. And it turns out it really doesn't matter which one I do first and which one I do second. I'm going to integrate that expression or that function first from 0 to 4, which means I'm integrating with respect to x first. And then I'll integrate from 0 to 2. That means I have to integrate with respect to y second. Again, be careful about doing this in general. Sometimes people will flip-flop these. Again, x corresponds to bounds from 0 to 4. Y corresponds to bounds from 0 to 2. Now I can do my integration. So I just do it like we've been doing. Again, the inside component is what I'm looking at first. The antiderivative of that with respect to x is going to be 1/3 x to the third plus 3y squared times x. I'm going to be plugging in a 4 and plugging in a 0. Again, that's into the x variable because I just integrated with respect to x. Thought I was out of that. Once we plug in a 4, we get 1/3 times 4 to the third power plus 3y squared times 4. When I plug in a 0, I get 1/3 times 0 to the third power plus 3y squared times 0. Doing the algebra, once you take 1/3 times 4 to the third, that is a 64/3. When I take 3y squared times 4, that's just 12y squared. And then this whole thing will become a 0. And so that's what I'm integrating with respect to y. When I do integrate that with respect to y, I'm just going to take the antiderivative, that's 64/3 times y plus 4 times y to the third. Again, I'll plug in 2 and I'll plug in 0. Plug in 2 first. That's 64/3 multiplied times 2 plus 4 times 2 to the third. Whoops. And when you plug in 0, just to save myself some time, plugging in 0 for y gives me 0 plus 0, so that just gives me 0. I won't write all that. So 64/3 times 2 plus 4 times 2 to the third. That gives me 74 2/3. Or about 74.67. And that tells me that the value under this surface over this rectangular region is 74 2/3. Let me show you that region on a graph. All right, so here is that surface, an elliptic paraboloid pointing up in the air. Now, you'll notice I want to point out that there's nothing below the XY plane. So all of the volume here, all of the signed volume is going to be counted as a positive. All right. So here's the surface, and I'm looking at a specific section under the surface. I'm going to have to zoom out quite a bit. But I'm looking at a specific section under the surface, whoops, specific region of the plane that's just this little rectangle here. It's hard to see. Let me do it that way. It's hard to see, and when you scroll in too far, it cuts off this little corner on me. So that's this little rectangle, X going from 0 to 4, Y going from 0 to 2. So we're asking, what is the volume of the part of the volume under the surface over that little rectangular region? And if you sort of look at that, again, here's my surface total. We're looking at the object under the surface, but over the XY plane, determined by that little rectangle. So we're looking at this specific three-dimensional object that I have written here in green. Obviously, some of it, a little bit of it is off, but you can see this object here. It's a three-dimensional object. It's the part, it's the object under the surface, but that's just over that rectangle in the plane. So the volume of that's what we just found, and we just found that to be 74 2/3. Okay, so hopefully that makes sense. The volume of this object here is 74 2/3. So that is the volume under the surface, x squared plus 3y squared, but over the rectangular region in the xy plane, bounded with x between 0 and 4 and y between 0 and 2. Now let's check out another one. Let's find the volume determined by the following integration. Now this integration gives me a surface generated by z equals y to the third times sine of x. And we're integrating with respect to x from 0 to pi over 2. And we're integrating with respect to y from 0 to 8. By the way, integrating from 0 to pi over 2 and then integrating from 0 to 8, if you drew that out in the xy plane, you just get a rectangle where x goes from 0 to pi over 2 and y goes from 0 to 8. So the rectangular region, or excuse me, the region we're integrating over is still rectangular because of these bounds. X going from 0 to pi over 2, y going from 0 to 8. Now we're just asked in this case to find the value, so that's what we're going to do. We're going to integrate from 0 to 8 eventually, but our first integration is going to be from 0 to pi over 2. And when you take the antiderivative of sine, you get negative sine. Again, y to the third is just a constant with respect to x. So we're taking the antiderivative of sine of x, and that's going to give me y to the third times negative cosine of x. I'll put the negative out front. And obviously we're integrating that from 0 to pi over 2. Remember always, since we integrated with respect to x, I'm going to plug the pi over 2 in for x. I'm going to plug the 0 in for x. So my integration from 0, I messed that up, excuse me. My integration from 0 up to 8, well, it's going to be negative y to the third times cosine of pi over 2. Now, when you take the cosine of pi over 2, I get a 0. So I'm just going to write down 0 there. Minus negative y to the third times cosine of 0. If you type in cosine of 0 into your calculator, or if you just look at the unit circle, you'll see that cosine of 0 is 1. So you get negative y to the third times 1 when you plug in 0. Doing that calculation, the first bit gives me 0, and then the second bit gives me a positive y to the third. So I get the integration from 0 up to 8 of y to the third with respect to y. This is just a polynomial integration. Y to the third, antiderivative, one antiderivative is 1/4 y to the fourth. Again, we're going to go from 0 to 8, so I plug in an 8. When I plug in an 8, I get 1/4 times 8 raised to the fourth power. When I plug in a 0, again, saving myself some time, I'm just going to say that you get a 0. So 1/4 times 8 to the fourth power becomes 1024. And so the area, excuse me, the volume under that surface, but above the XY plane, is 1024. The signed area, I should say, is 1024. So that's the idea in that case. Hopefully that makes sense. Signed area here is 1024, or signed volume. Keep saying area. Signed volume is 1024. Now, I'm not going to draw this figure and the volume of the figure that we just calculated, because that doesn't give me really any insight beyond the drawings that I've seen previously. So let's just go on to the next example. Let's find the volume determined by this integration. We're integrating y plus 3, first with respect to y, from negative square root of 9 minus x squared to positive square root of 9 minus x squared. And then we're integrating with respect to x from negative 3 to positive 3. So let's do the calculation, and then I'll talk about what we're integrating over here with this type of integration, what region we've just integrated over. But first, let's do the calculations. All right, so the first thing I'm going to do is I'm going to do my inside integration as usual. And the antiderivative with respect to y, be careful about this. Last couple I've done with respect to x first. Here we're doing it with respect to y. Antiderivative with respect to y is going to be y squared plus 3, or 1/2 y squared plus 3y. Plugging in my bottom bound of negative square root of 9 minus x squared, and then plugging in my upper bound of a positive square root of 9 minus x squared. Once I've done that, then I'll integrate with respect to x. I guess I should put an equal sign up front here, but that's okay. Now, when you plug in the square root of 9 minus x squared, the positive square root, well, first off, let me well, that didn't work. There we go. So I'll plug in the positive square root first. I get 1/2. When I plug in the positive square root and then square it, I just get 9 minus x squared. Plus 3 times the square root of 9 minus x squared. Oops. That's what happens when I plug in the positive square root. When I plug in the negative square root, well, the first component's exactly the same. 1/2. When I take a negative square root of 9 minus x squared and then square it, I just get, again, 9 minus x squared. However, when I plug in negative square root of 9 minus x squared in here, negative times 3 gives me a minus 3 times the square root 9 minus x squared. Now, this is a lot, but I'm going to do this all in one step. This 1/2 times 9 minus x squared is going to cancel out with this minus 1/2 9 minus x squared. So those two initial terms are going to cancel out. When you take a 3 times the square root, this is minus a negative 3 times the same square root. So we're essentially taking 3 plus 3 times this square root. That's going to give me 6 times the square root of 9 minus x squared. And I want to integrate that with respect to x. Now, at this stage, you can do a couple of different things. You could, by hand, find the antiderivative of 6 times the square root of 9 minus x squared. Or you may have gotten sick of doing antiderivatives already. And you may say, well, can't I just use technology to calculate whatever this is, or at least get a good approximation of whatever that is? And you can absolutely utilize technology to simplify your work. In fact, most of the time, people do just that. There are some things you have to be a little bit cautious of when you do use technology, like the way a calculator works is not by finding the antiderivative, but doing approximations. But if you utilize your calculator to do this definite integral, or if you use some other thing like a website, or even Desmos will, I believe, do an antiderivative or find an integral right there. But what I got through my graphing calculator is about 84.82. There's some other little tricks that I'll show you once we get a little bit beyond what we're looking at here. So you get about 84.82. Now, that was some sort of a volume here. By the way, I could not have, some calculators, I could, integrate this interior piece as well. On my graphing calculator, I can't do that. I have multiple graphing calculators, but one of them, the one I primarily use, I can't do that because it doesn't have numerical bounds here. The other one I can do, if you have a CAS computer algebra system, oftentimes you can do that. But with numerical bounds, most graphing calculators will do a definite integral with numerical bounds. Okay, so anyways, I get 84.82, and that I know is the volume of some object. It's the volume of an object z equals y plus 3, that's a plane, over some region determined by these bounds. Now, let me show you that region first, and then I'll talk about the three-dimensional idea. So I'm graphing this in 2 dimensions. I just want you to realize that y equals negative square root of 9 minus x squared. That's the lower half of the circle of radius 3. And y equals 9 minus x squared is the upper half of the circle of radius 3. So when we were integrating y from the negative square root of 9 minus x squared up to the positive square root of 9 minus x squared, we were going from the lower half of the circle to the upper half of the circle. And our x values were between negative 3 and 3 because that's where we were ending. So the region we were actually graphing over was the region enclosed by that circle. So we were graphing over, we were looking at the section of the graph over this region in the XY plane, over the circle in the XY plane. Now the surface, f of xy equaling y plus 3, that's just this plane right here, this plane on a diagonal. And what we were doing is we were finding the area under this surface over the circle in the XY plane. So let me rotate this a little bit. So if you look down along the z-axis, the part of the plane that's under the circle is a 3-dimensional object, and we found the volume of that 3-dimensional object. This thing here. Okay, so it's essentially sort of a slice of a tube. That's what we're looking at. Now, we were fortunate that there was never a point over the region that my plane went under the XY plane. So my surface didn't go under the XY plane in this region. If it did, that part would have been counted as a negative. So that's the idea there. That's what we found. And we said that this volume was about that 84 number, about 84.82. Now, a couple things I want to say. Obviously, we integrated. We did a double integration. We found the volume of this object, the volume under the surface in the region above this circle. And when we did that at the end, we used our calculator to help us. We could have, if we wanted to, use the calculator to help us in this one as well. And we could have used it in our first example as well, if I had wanted to. In fact, in those two examples, I could have, in a lot of ways, simplified by using my calculator. Now, before we go ahead and try to simplify using some technology, I want to point out some of the properties of double integrals. If we're looking at double integrals and properties of double integrals, many of the properties of double integrals will be similar to the properties that we have seen on our standard single integration. So let's let f and g be continuous functions defined over a closed bounded region R. And let's let c represent some constant real number. When I integrate, I can take any constant multiple and pull it out of my integration and pull it out in front of my integration. Again, that was something I could do when I integrated with respect to x, something I can do when I integrate with respect to y, and now that's something I can do when I integrate with respect to whatever area that my region is covering. Sums of functions also work in the same way. If I want to do a double integral of a sum of f plus g, I can integrate f and then add the integration of g as long as I do it over the same region. So as long as we're integrating over the same region, I can integrate f first, integrate g first, and works the same way. Also, let's assume my bounded plane region R actually consists of two parts, an R1 and an R2, where the R1 and R2 do not overlap. If I'm integrating a function over a region and the region can be split into two pieces, then I can integrate over the first region and then integrate over the second region, add them up, and that's going to be the integration over the combined region. Also, if I have two functions and one of them is greater or equal to the other for all points in the region, then the double integral over the region of f has to come up to be greater than the double integral over the region of g. So the double integration. And this is pretty obvious. Think about these as surfaces. We're saying if this F is surface is always higher than the G surface, then the volume is always going to be bigger. So if for every point in the region, F is higher than G, then the area, the volume of the object under F is going to be greater than the volume of the object under G. That should be fairly self-explanatory. Now, before we move on and utilize some of those properties, I want to go back to this example, example 2, and show how some of those properties combined with technology can make our lives a lot easier on some of the double integrations. So we were finding the volume under the surface over the rectangular region with these bounds. And we did that using sort of the longhand way of doing that. Did that all by hand earlier. Now I'm going to take advantage of some technology and what I know about the properties of double integration and some of the properties of single integration I'll use as well. So let me do a double integration. Now I know that last time I believe we integrated with respect to X first and then with respect to Y. Here I'm going to do it with respect to Y first and then with respect to X. But with rectangular regions, you can kind of flip them as long as you flip both the bounds and the dx dy if you like. So that's what I'm going to do. So here's the deal. Let's use some properties. One of the properties said that if I want to integrate, I can integrate if I have sort of two functions that we're adding inside, then I can integrate, do a double integral of the first function. So I'm going to do a double integral of dx squared plus, then I'll do a double integral of the 3y squared. This is where I can start utilizing some of my technology pieces. So let's start, I think I want to start over here on this right-hand side integration. Ooh, that does not. All right. This whole thing is a definite integral with only y's in it. So I can use technology. Since I have bounds from 0 to 2, I can integrate from 0 to 2 that 3y squared with respect to y. And that'll give me an 8. So what I ended up with is this whole piece. Whoops, let me rewrite that. This whole integration becoming an 8 dx. So I could have used technology to compute this piece. And that piece gave me an 8. Now I can be a little bit clever over here and utilize technology for this piece as well. Let me actually just copy and paste. And here's how I'm going to do it. I know that the first thing Let me re-say that. Well, that didn't work at all. I was trying to get my parentheses around there. That's okay. So this integral that is highlighted, I'm integrating with respect to y. Now I might see, oh, this has an x squared in it, so I can't use my technology. But since I'm integrating with respect to y, this x squared is a constant. So what I can do is I can treat that x squared as a constant and pull it out front of the integration with respect to y. Now, because it's not a constant with respect to x, I cannot pull it out front of the integration with respect to x. I can't pull it all the way out front. I can only pull it out front of the integration with respect to y because with respect to y, x squared is a constant. And this thing I can absolutely use technology on. So you just integrate from 0 to 2, 1 dy, and you get a 2. So what we've done utilizing some understanding of pulling constants out, splitting up our terms, integrating with respect to y. We use technology to shorten the process, and now we're just integrating with respect to 2 from 0 to 4, and or did I say integrating with respect to 2x squared, sorry, 2x squared from 0 to 4, and integrating from 0 to 4, we're integrating 8. Again, can't forget that x squared. I pulled it out. Think of it. So this whole thing became a 2, and I got 2x squared. All right. And now, once again, I can use technology. I can integrate from 0 to 4 that 2x squared with respect to x and get a 42 and 2/3. And then I can use technology and integrate from 0 to 4 that 8 with respect to x and get a 32. And sure enough, when we combine those, we get 74 and 2/3. So using the properties of integration and technology can really save us some time if we're clever about it. Again, I'm not sure what's happening here. That's not. There we go. So that whole thing inside the parentheses became a 2, and so I got 2 times x squared. Hopefully that all makes sense. So using some of those properties along with technology can make my life a lot easier and make this process a lot quicker. Now, I essentially just use a couple of these properties. The constant multiple I kind of used. The sum of functions I definitely used. I didn't use the sum of regions yet. This fact is something you should know, but it doesn't necessarily help you in calculation of a specific function in the usual case. So let's do one where I have to combine regions. Let's integrate 4x minus 7y with respect to some area over the given region. This dA just means with respect to area. The dA when you're using x and y's are going to be either dx dy or dy dx. So we're going to take this region that's in this picture. Now, there's a couple of ways I can do this. If I want to integrate, or if I want to get this region, one way I can do it is to split it up into two regions. I can go from x value from 0 to 2, and then my y value is going to go from y equals 0, which is the x-axis, up to the parabola. Now this parabola is y equals x squared. That's pretty obvious because it's a parabola going through 0, 0, and 1, 1, and 2, 4. Hopefully that's pretty obvious. So that's y equals x squared. This line is the line y equals negative 1x, slope here is negative 1, negative 1x plus 6. Okay, slope of negative 1. And if you extend this, you can see it goes through 0, 6. You can also look and see it goes through the 0.33, goes through the 0.42. So you could come up with that line in a number of different ways. So you could break this region up into two component parts, the one from 0 to 2, and then the other one goes from 2 to 6, and we're under the line. So if I wanted to do it that way, I could do it that way. Another way I could break this region up is to say, well, let's go left to right first. This goes from this line on the right over to this parabola. And the y values go from y value of 0 to a y value of 4. We'll actually do this both ways. We'll break up the region into two parts. And we'll go y first and then x. And then we'll do one region where we do x first and then y. So we integrate with respect to x and then y. And in both of them, we'll use some technology to help us quicken our result. All right, so let's, I'm gonna write some things down as I do this. We have y equals x squared as one of the curves, and the other curve is y equals negative 1x plus 6. That's the line here and the parabola there. So we have that, and the other again, this is my region in the two-dimensional plane. My other significant line is the x-axis, which is the line y equals 0. Okay? So this is sort of a triangular region. I can break up my triangle into two pieces. If I want to integrate with respect to y first, I can go from y equals 0 up to y equals x squared on this first part. And then I can go from y equals 0 to y equals negative 1x plus 6 in the second part. In other words, what I'm doing is I'm breaking up my region into two component parts, one here and one here. And I'm going to take this first region and the second region, and I'm going to calculate the volume of this, the volume of the three-dimensional object under this surface, but over the two regions separately. That is a signed volume, so I might get a negative number. But I can do that by breaking it up into two regions. So let's do that first. That's the way I'm going to go about this first. So if I do that, my integration, I'm just going to put 0 and 0 as my bounds right now, and then I'll sort of talk through my bounds. Integration of 4x minus 7y. Let's say I want to integrate, well, I do want to integrate with respect to y on the first region, and then with respect to x. And then we'll do the exact same thing for the second region, the R1 and the R2 that I had just laid out. Now on this first R1, with respect to y, we're starting at y equals 0. That's good, y equals 0. And we're going up to y equals x squared. The x value on that first region goes from 0 to 2. On the second part of the region, the R2, we're going from a y equals 0 up to the line y equals negative 1x plus 6. So we're going to go from 0 to negative 1x plus 6. And we're integrating the x value from 2 all the way to 6. Notice that when we are doing this type of integration, my outside integration, if I want to find an actual value, has to be numerical values. My inside could have expressions in it. Now, in both of these cases, we are going to integrate (4x minus 7y) with respect to y. So that's going to give me 4xy minus 7 halves y squared. In the first one, I'm going to go from 0 up to x squared. In the second one, I'm going to get that exact same thing, 4xy minus 7 halves times y squared. I have a little bit of mistake there. That didn't compile the way I thought it was going to. And that's going from 0 up to negative 1 x plus 6. Now, sadly, again, I probably should have said this before I actually integrated. I'm doing this by hand because a lot of graphing calculators won't have the technology ability to do this using the calculator because we have an x squared as one of our bounds, and in this one, because we have a negative 1x plus 6 as one of our bounds. So that's kind of a sad part about this. It's all right, nothing too crazy. My first integration, when I plug in an x squared, I get 4x to the third minus 7 halves x to the fourth. That's what happens when I plug in an x squared. When I plug in a 0, I just get 0. Again, I'm plugging that in for my y value. And then I'll be integrating that with respect to x. On my next one, when I plug in negative 1x plus 6, I get 4x times negative 1x plus 6 minus 7 halves times negative 1x plus 6 squared. And then when I plug in 0, I guess get a 0. That's nice. Integrating that with respect to x. I am going to clean this up, this second one up just a little bit. I already simplified the first one, so I can just go ahead and leave that one alone. 4x to the third minus 7 halves x to the fourth. By the way, hopefully you see where that's coming from. Maybe I'll go back up. This is 4x. I'm replacing this y with an x squared. So I get 4x and I'm replacing the y with an x squared. And then I get 7 halves y squared. And it's basically I'm replacing the y with an x squared. So x squared squared becomes x to the fourth. 4x times x squared becomes 4y, x to the third. If that wasn't already obvious. Then we're integrating from 2 to 6. And I'm going to clean this up a little bit, not too crazy. But this is negative 4x squared plus 24. And I think I'm just going to leave this in, minus 7 halves times negative 1x plus 6 quantity squared. The reason I'm leaving that as messy and not multiplying it out is because I don't plan on doing this by hand at this stage. You could multiply this polynomial out, simplify this whole thing, and then do that by hand. But what I am going to do is I'm just going to plug this into my calculator. When I integrate, and when I do that first integration, the integration from 0 to 2 of 4x to the third minus 7 halves x to the fourth with respect to x, I get a negative 6.4. So that one must have been under the xy plane. And then when I get my second integration, this is where technology really saves me a lot of time. I take negative 4x, oops, that should have been plus 24x, excuse me. Negative 4x squared plus 24x minus 7 halves times negative 1x plus 6 quantity squared integrated with respect to x, I end up with a 32. When I add those two together, I end up with 25.6. So while in the middle, my calculator didn't help me do this stage, it absolutely helped me a lot with this second stage. So we get 25.6 as the volume, the signed volume under this surface and over this region in the XY plane. And you can see that some of it kind of dips below. Now, that's one way. I know I'm taking a minute, but I'm going to do it the other way too. I'm going to integrate first with respect to X, then with respect to Y. Well, if I'm doing this with respect to X, I can go from this curve to this curve. And then with respect to Y, I can go from 0 to 4. So I can go from this curve, the negative 1x plus 6 down to the x squared curve. Just note that if I'm going to do this with respect to X, when I have Y equals x squared, and now I want to integrate with respect to X, I better change that over into an equation which has X equals a function of Y. And similarly, if I solve for X, I would subtract 6 from both sides and then multiply both sides by a negative 1. It turns out if you solve for X, you get X equals Y minus 6 times negative 1 is negative 1Y plus 6. That one's kind of an interesting one that usually doesn't happen with. Trying to get that spaced correctly. There we go. That you can't generally just switch the X and Y, but it turned out when you actually solve this one, it did do that. So anyways, what are we saying? We're saying that if we're willing to integrate with respect to Y second, Y is going to go from 0 to 4. And if we're going to integrate with respect to X first, the bounds, the upper bound with respect to X is negative 1Y plus 6, and the lower bound with respect to X is X equals the square root of Y. Again, this is what happens when I integrate with respect to X first and then integrate with respect to Y. So I could do that, and I'm going to do that as fast as I can, just so that I know this one is a very long example. That's okay. It's got a point. Integrate X, I get 2X squared minus 7XY, or minus 7YX, doesn't matter, from the square root up to the line, which means we're going from, the square root of Y up to the line of negative 1Y plus 6. Again, we're plugging these in for the X. So we end up with 2 times negative 1y plus 6 squared minus 7 times negative 1y plus 6 times y minus, when I plug in square root of y, I get 2 times square root of y squared is just y to the first minus 7 times the square root of y times another y. I'm going to rewrite that so I don't get confused. And I'm integrating that whole thing with respect to y. This might look really, really ugly, and it is. It's a really, really ugly function. If I had to do this by hand, this integration by hand, I would want to simplify it and rewrite and multiply things out. But if I have technology, it's not that bad. I can take the entire function just like it sits here, plug it into some technology component, maybe my calculator, maybe some other thing that does integration. Maybe you simplify it a little, maybe like you distribute this negative sign so it's not that, or maybe you distribute this thing. But when it's all said and done, I can type that into my calculator. And sure enough, when I did this on my calculator, as it sits, I got about 25.60 if I round to 2 decimal places. My calculator didn't give me exactly 25.6 because the way the calculator operates, it does successive approximations, but it's 25.6 when we did that. So I got the same thing both ways. 25.6, 25.6, whichever way I did that. And now you see that we can, first off, we can split our region into parts if we need. Our region that we're integrating over, we can split that into parts if we need. Second, we see that sometimes there are parts of our surface which go below the XY plane, and so we might end up with some negative sign value. That's the part that goes below the XY plane. Or at least in this region, we had more going below than we had going above. And we also saw how when I integrate with respect to y, then with respect to x, you'll get the same answer as when you integrate with respect to x and then with respect to y, as long as the bounds are correct. So as long as we have these bounds correct, we can integrate either way. So that was the idea of this here, this problem here. Now, that change of integration and rewriting our integration, that actually is a very nice feature because there are some double integrals that if we try to integrate with respect to x and then with respect to y, this becomes a very hard integral to integrate if you do it with respect to x first. But if we change around and we integrate with respect to y first, then this is actually doable. So just take a moment to say, think to yourself, we have a constant over x squared plus another constant if we're integrating with respect to x. The antiderivative of that is going to be something akin to like arcsine or arctangent. I forget what it is, but it's rough. It's not a nice one to deal with. But if I integrate this function with respect to y, since I have a 2y on top, that's the derivative of this function below. That is the derivative of this function below with respect to y. So a simple u substitution will be, I'll be able to integrate with respect to y. Now I can't just flip-flop my x and y because these bounds are important too. So I am going to have to figure out what region we're talking about here so that I can flip-flop correctly. Flip the x and y. I'm going to have to rewrite my regions and my region bounds. Now, before I start drawing this, the region is going to go from, well, the x value is going to be between x equals y to x equals 1. And the y values are going to go from y equals 0 up to y equals 1. X equals y, same thing as y equals x. That's the line of slope 1. So if I were to draw this, it would be a line of slope 1. X equals 1. That's a vertical line. From y equals 0 is the x-axis, to y equals 1, I'm getting this closed triangle. So I'm getting that bounded region bounded inside that triangle. By the way, this point over here is the origin. I probably should have stated that. This is the origin here. I didn't want to draw my y axis, but that's what it would be. So how would I integrate the other way? Well, again, this is kind of going from x value of y to x value of 1. That's left to right. What if I go from bottom up? Well, that's a y value of 0 to a y value of x. Y equals 0 to y equals x. That's again from bottom up. And then from left to right, the x values go from 0 to, remember this was an x value of 1. And we're at the point 1, we're 1, 1 over there as well. So the x values are going from 0 to 1. So there you go. That's the region. And now I know that if I want to integrate with respect to y first, and then x is going from 0 to 1. Y is going from y equals 0 to y equals x. By the way, they don't always come out quite this nice. Obviously, in this case, it came out very nicely that these were exactly the same. A lot of times they don't. But here we're integrating with respect to y first, and then with respect to x. if, I'm going to erase this picture. If I want to integrate with respect to y, I'll do a u substitution. U equals y squared, and then du is equal to 2y times dy. Wouldn't you know, I have a 2y dy. So this whole integration, well, my integration with respect to x doesn't change. My integration with respect to u will change, but I'm going to leave it blank right now. 2y dy becomes 1 times du. So 1 is going to be my numerator. I'm going to change that 2y times dy to a 1 times du. And in the denominator, this x squared plus y squared is going to become an x squared plus u. When I integrate that, that's going to become natural log of x squared plus u. And then I would divide by derivative inside function, but with respect to u, derivative is just 1. So just natural log of x squared plus u. All right. And I'm going to integrate that with respect to x after I do some plugging in. Now, instead of, this is the antiderivative. That's the antiderivative. I'm going to plug in some values. Whoops. But before I plug in those values, I'm going to switch it back to, I'm going to switch my u back to a y squared. So going to do a lot of stuff here. Go from 1, integrate from 1 to 0. This is the natural log of x squared plus y squared. Plug in a y value of 0 to a y value, y equals x. So plugging in 0, plugging in x, or plugging in x first and then plugging in 0. If I plug in an x first, I'm going to get the natural log of x squared plus x squared. So I'm going to get the natural log of x to the 4th. Oh, did I say x? I didn't say x squared squared. I'm sorry. I said x squared plus x squared. That would be 2x squared. Excuse me. When I plug in 0, I get natural log of x squared plus 0. And I'm going to integrate that with respect to x. Now you can do this on your calculator right now if you'd like, using technology. You can also use some rules of natural logs to simplify that. So again, either way, if you want to do it using technology, go right ahead. Take natural log of 2x squared minus natural log of x squared. Integrate that with respect to x from 0 to 1. And that's perfectly fine. But like I said, if you wanted to do this by hand, this is also pretty easy to do by hand because When you integrate from 0 to 1, you can use a rule of natural logs, which says natural log of something minus natural log of something is the natural log of the quotient 2x squared over x squared. That's one of the rules of natural log. That's a quotient rule. And you'll notice that the x squared over x squared is going to cancel are going to cancel out. And basically, you're just integrating from 0 to 1 natural log of 2 with respect to x. This will give you, this is just a constant, so you can even pull this out front. You're going to get natural log of 2 times x. As the antiderivative, plug in 1, you just get natural log of 2. Plug in 0, you just get 0. So you end up with just the natural log of 2 as your final answer. So again, being able to change our region over allows me to integrate this. If I tried to integrate this with respect to x, it'd become very cumbersome. Now you may think this is cumbersome, but just wait and try to integrate that thing with respect to x first. It's much worse. And this one is all doable by hand and very easily doable by hand if we change the order of integration from x first then y to y first then x. Again, I have to be very careful how I set up my integration bounds though, whenever I do that. Now we've done a lot of double integration so far. We've done a lot of examples of double integration. Double integration finds the value. It specifically finds the value of the three-dimensional object under my surface over the region that I'm looking at, over the region I'm integrating through or around or above. Another application we can do is we can find the average value of a function over a given region. And if we do that, well, the average value is just going to be the volume that we calculated in this video divided by the area of the region. And if you recall, the area of the region is just the double integration over the region of 1. We saw that in the previous video we did. So if we do a volume calculation divided by the area, this is a 3-dimensional divided by a 2-dimensional, we're going to get a single dimensional that is going to give me a value that's the average value of my function over the region. Hopefully that makes sense why that is. Again, here is all the values divided by the area of the region we're integrating over. So that'll give me the average value of f over the region R. So let's look at an example where we're asked to find the average value. This says find the average value of the function 3xy squared over the region bounded by y equals 0, x equals 6, and y equals x. So let's go ahead and do that one. All right, the first thing I'm going to do is decide what this region looks like so I can understand the bounds. Y equals 0 is the x-axis. I'll draw the y-axis there. Y equals x is a line of slope 1 going through the origin, and x equals 6 is a vertical line. Ooh, that was a bad one. Vertical line there. So our points are at 6, 6, 6, 0, and 0, 0. We have a triangle here. Okay. So in terms of the integration, when I'm setting up my integration, let's say I want to integrate first with respect to y. That means I'm going to go from y equals 0 to y equals x. And then I'll integrate with respect to x. That'll go from 0 to 6. So 0 to 6 integrated with respect to x. And then, well, first I should say, going y equals 0 to y equals x, integrating with respect to y. Since I'm integrating this function 3xy squared, 3xy squared, that's what it looks like. All right. Now, this probably looks familiar. This is an integration that we've done before. We did this at the very earliest example. Although we integrated with respect to x first and then y, and there's some changeover, but it looks very similar. I'm going to use technology to figure out that volume as quickly as I can, as much as I can. Okay, so when we integrate with respect to y, I get y to the third divided by 3. So essentially that's just x, y to the third. I'm going to plug in 0, going to plug in x. When I plug in x, I get x to the fourth. X times x to the third is x to the fourth. When I plug in 0, I get 0. So we're going to be integrating this, integrating x to the fourth with respect to x from 0 to 6. Again, I'm going to use technology to simplify as much as I can. I get 1555.2. No, this wasn't something we did earlier, was it? No, was not the same region we dealt with earlier. Sorry, I thought that looked familiar, but it is definitely not the same region. Okay, from y equals 0, x equals 6, y equals x. Yeah, that triangle there. Good. So the other region must have been a different triangle. Not sure which one, but would have been a different one. By the way, so this is the volume. In order to find the area, I'm essentially going to do that same integration, but not with the function 3xy squared, but just with the function 1. So that's the area right there. When you integrate 1, you just get y. Plugging in 0, plugging in x. When you plug in x, you just get x. When you plug in 0, you get 0. So that's just 1 times x integrated with respect to x. And if you want to use technology, you can. This one's pretty easy to do by hand as well. I'm gonna get rid of that drawing. So I don't know, might as well use technology. Integrate from 0 to 6 x dx. That gives me 18. So that means the average value of the function over the region R is 155.2. That's the volume divided by 18. That's the area. 155.2 divided by 18 comes out to 86.4. So the average value of this function over the region R is 86.4. Again, it's this function average value over that region. I forgot to say this, and I should have said this earlier. Here I used this double integral to calculate the area. But remember, what we were talking about here was just a triangle. And so if you wanted to, you could have said, well, the sides of this triangle are both 6. 1/2 base, this was a right triangle, so 1/2 base times height would have been 1/2 times 6 times 6. You would have gotten an 18 that way too. So if you want to calculate the area, obviously the integration will be able to do that for you. But sometimes, like in this case, it's just a triangle. The area of a triangle we know is 1/2 base times height. So 1/2 times 6 times 6 would have been 18 as well. So if you wanted to calculate area in another way, you could have done that too. All right. Let's take this example. Let's find the average value of the function f of x, y is equal to y plus 3 over the region bounded by the circle of radius 3. So the interior of that circle of radius 3. Now this should look very familiar because in one of the previous examples, I made a point to say, oh, this was the circle, this bounding was the circle of radius 3. So we can utilize this previous work because we already found the value and then find the average value. Let's go ahead and do that. All right, so again, we're going to utilize some of the stuff we did earlier. The value we already calculated because we've calculated this integration. We've integrated y plus 3 with respect to y from negative root 9 minus x squared to positive root 9 minus x squared. Again, that's with respect to y. And then with respect to x from negative 3 to positive 3. Now, I said that we got approximately 84.82, and that was right. We got approximately 84.82, but in reality, what that number was actually exactly 27 pi. So if you actually calculated what it was 27 pi. 27 pi gave me that 84.823, blah, blah, blah. So that was the precise value. By the way, this is a circle of radius 3. Hopefully we know that the circle of radius 3 is pi r squared. So if I'm really clever, I don't have to do the integration again. I could if I want to. It's not hard to do, this integration, but this is a circle of radius 3. Therefore, it's going to be pi times 9, times 3 squared. So pi times 9. So if you want to find the average value over the region, a real quick way to do that, since we already knew the volume was 27 pi, and we could calculate the area easily as 9 pi, the average value is simply 3. Again, if you want to find the area by taking this double integration, but just integrating 1 with respect to y, and then with respect to x, you'll still get 9 pi. But you can also do this by just understanding the geometric formula for the area of a circle, pi r squared. So again, quicker ways to do this sometimes. Sometimes that doesn't always work. Sometimes the area is not going to be super easy geometrically to calculate, and then you have to use this one. But in this case, it was real nice. So that's how we find the average value of a function. So that'll be the last example in this video. Obviously, we did some average value. In the previous video, we did the area of a region. We learned how to utilize some of these rules where we can pull out constants and do sums to make our lives a little bit easier, especially if we have technology. But mainly, what we figured out was that the signed volume under our function, but over the region we're integrating over, is what we get when we do these double integrals. We're not going to do we're not going to do any other examples in this particular video, but this will be a key feature, these double integrals, moving forward in this section. And so in some of the next videos in the playlist, you'll see those. All right. So that's double integration and value.